So I've got this lamp. So this is a pretty crude lamp, as you can see. There is just a couple of bare electrodes hooked up to a ballast to get a super high voltage, and then plugged into there, which is why there's all these danger signs about don't stick fingers in there because it would be really, really bad. This is what we talked about as a tube of gas. So this is a tube filled with hydrogen gas, and at each end are some metal electrodes. So we pass a really, really high voltage across, or put a really high voltage across this tube of hydrogen gas, and that excites the molecules as we talked about in class. And so let's do that. All right, so you see that color coming off the hydrogen? Don't stare at it too much because it does have UV light coming off of it also. Now, we know, it looks just like, some kind of nice red light. We know that it's actually a series of spectral lines. That is, only certain energies are actually coming off of that. We can measure that with this device here. So this is a fiber optic cable that is feeding into a spectrometer, which is this little box right here. A spectrometer is just a device that can separate the light into its constituent wavelengths and measure the intensity of each individual wavelength. So that's going into the computer. And then I've overlaid the spectrum. We can get rid of that too. I don't remember how. Anyway, if we need to. But that tells you like which color of the spectrum we see. So if we start collecting the data, maybe we should see some. Oh, there it is. Okay. So there's the spectrum coming out from that light. And is it still collecting? Okay, yeah. So it's updating every so often. It's not great. Let's see if we can point it a little bit better in there. Trying to get some better signal to noise. There we go. All right, so you see these individual peaks that we see here? That's evidence of these individual spectral lines coming off of the hydrogen. In other words, if this were a regular tungsten filament, which I don't think we have here, you should see just kind of a big arc of all the possible wavelengths. The fact that we only see a few of them is because of those energy levels. And so that's what's happening. All that stuff we've been modeling in our equations, that's what that's showing, these different energy transitions. This is not too hot. Yeah, it is. All right, so I'll give that a second, and then we can look at some of these other types of gases so like krypton, carbon dioxide, helium, and we saw that, I mentioned that different types of atoms are going to emit in different ways. The spectral lines become both more complicated and less predictable as we have more than one electron. So all those other ones we're going to try have more than one electron. We can try here to see if we can get some data. Let's stop this collection and try a new.
I think maybe if you go to like collect more, it should say you want to erase it and they already had.
Oh yeah, it will. I'm just trying to see if I can get it to go to update more more quickly. but I don't know if we have the other software on this computer. We might have to find it on the other ones, because it should update a little faster than that. But let's try one more time. And let's see what happens when we point this thing up at the fluorescent lights. So we should just kind of get a general spectrum here. There we go. So you can see it's kind of a crazy looking spectrum, because I'm not sure this one is quite set up for this way. But you also see some lines. You still don't see that continuum, and that's because these are also atomic emissions. We talked about the mercury gas that's in the fluorescent lights, and that's why we see these peaks instead of kind of just a broad emission spectrum. All right, let's cool down. So what do you want to see next? We've got helium, krypton, carbonic acid, argon, carbon dioxide, hydrogen, more hydrogen, more hydrogen. What's your favorite?
Krypton.
Krypton? All right. Why is that your favorite? Superman? Yeah. I'm always afraid I'm going to break these things. Okay. What color do you think it's going to be? I don't know. Any guesses? So I don't know what's going on with the 0 point here. Why it's showing absorbances below 0. I don't know if there's some kind of calibration that we need to do or what. You know, there are directions. Maybe if I read them. Let's see. Change units. There we go. A little better. Let's try again. Oh, so I think we might be getting some interference. Okay, cool. All right, so you see that? that's the emission from krypton. So we once again see these spectral lines coming up. And this is also emitting significantly in the infrared. So just beyond the red that we see, we're also seeing the infrared. Well, we're not seeing it. We're observing it by measuring it in the spectrum because we can't see it because it's infrared. This is how those signs work, by the way. I know some people usually see that, the signs that are glass tubes that say beer or whatever open. I don't know. That's usually neon or krypton or argon, one of those types of inert gases that are excited with a ballast, much like a fluorescent light. All right. Let's see if we can get a better read on the fluorescent lights now that I've got this thing corrected. I'm not sure we'll see anything different, but we might have to get this thing closer. Oh, you can see it. There it is. So there are some of those spectral lines from the fluorescent lights. We see a little bit broadening. Oh, yeah. Yeah. So you see some of that broadening because these lights are designed to have as broad of a spectrum as possible, because that makes them look nice and don't look as kind of weird and fluorescent-y. Especially the ones that you get for your house are tuned and filtered so that they have kind of a pleasing light type color. Different colors of lights are better for different applications. This one you can see the intensity is so great it's actually going off the scale because of all the brightness in here. And that's why you see these flat tops to the peaks. Should we try one more? Yeah.
Why do like the new fluorescent lights take so long to?
Which ones?
Like the new swirly one, I think has something like that.
Oh, I would call those the old ones actually, because now everybody's going toward the LED instead, which is partially because of that problem. I believe it's a heat thing, an energy thing. You need to actually get this thing going, and because of their relatively small ballasts, which are the little electronic devices that increase the voltage significantly and kind of give it a boom. I believe because of somehow of that, I've noticed the same thing, that they need to warm up, especially in colder, like if you try to put one of those as an exterior light or in a garage or something like that in the wintertime, they take a while, even longer. Like they start out super dim and then they kind of get brighter as they warm up. So I believe it's just a heat thing that they have to warm up. And I think that's one reason that a lot of people are going to the LEDs instead, because they don't have that problem. All right, let's take a look at carbonic acid gas. So this is, as we know, carbonic acid, H2CO3, has quite a lot of atoms and electrons. So we would expect a pretty complicated or complex spectrum to come through here. Let's see what we got. We can keep the thing lit. Let's see. Might have some contacts, some issues with the contacts here. All right, looks like we're not gonna get that one lit up. I wonder if there's a little corrosion on the contacts or something. So what do you think? Helium, argon, or carbon dioxide? Any preferences? Helium?
What units is the intensity?
Right now, it is just relative intensity. So how intense is one relative to another, one being the highest. So it's like from 0 to 1, just how intensity are they in relation to each other, or how intense are they with relation to each other. Oh, that's a bright one. Yeah, that's a little too bright. So in order to see those, first of all, we might even be getting some leaking in from the fluorescent lights. But what we can do is we can figure out how to do it. We can decrease the sample time. So that sampled for 1,000 milliseconds, which is a second. If we decrease that to, say, 100 milliseconds, we'll get 1/10 of the intensity. We'll get it much faster. And that should bring down some of those high intensities that are too high. So you can see that. It also makes it move a lot faster. So there's that helium spectrum. We could really even move that down, bring that down a little more. Yeah, and there you see that emission is all really in the visible, strong purple line, blue, green, yellow, and then out into the red, and those mix to form whatever color we see as kind of, what would you call that color? Orange? Peach? Yeah, that's right. That's why I wore the shirt today. I knew the helium lamp was going to come out this color. We could also kind of move this away if we wanted to decrease that intensity. Wait, let's see that. Those lines come up. So tomorrow in lab, you're going to use these things, which is like a slightly lower tech, well, way lower tech, let's be honest, version of this, which allows you to manually look at a light source like that, and then there's a little scale on the other side. There's a prism that, or a diffraction grating that diffracts the light and projects the individual lines onto a spectrum. So you can see where those lines are. And you'll use that to look at a hydrogen lamp and find the spectral lines, and then compare them to the actual known spectral lines that we might see in something like this. And then you'll do the math on that and see how they prepare, or how they compare. All right. All right, we'll just let that cool. All right, so back to what we were doing the other day, yesterday. Talking about electrons and that sort of thing. This is nice. I didn't make it. It was here. I'll leave it there. Let's see where we go. I just got my flu shot over in health services. So if you haven't got your flu shot yet, stop over there and get one so you don't get sick. We talked about building up these electron configurations. So you can practice those in the homework. Look at different electron configurations of ions and stuff. And then what we're going to look at today is how those electron counts that we talked about before influence and allow us to predict atomic properties. And we're going to look at a few different ones. We're going to start with ionization energy. So the energy required to completely remove an electron from an atom or ion. How much energy does it take to remove an electron? It always takes energy to remove an electron, even for those types of atoms that we talk about as wanting to lose an electron, like the alkali metals. It still takes energy for them to do that. They can end up giving up energy in other ways in that process, but it ends up taking energy. So all of these numbers are going to be positive numbers in units of kilojoules per mole. So how many kilojoules does it take to remove an electron from 1 mole of these atoms? Now, we looked at that on the per atom basis with hydrogen, and we saw how many joules of energy it took to remove an electron from hydrogen. You remember doing that, where we looked at the infinity level and the subtraction as n1 goes to, or n2 goes to infinity. What the ionization, what that energy is, that would be the energy for one particular atom, and it was something like 2 × 10 to the minus 19 joules. So this is what we're talking about, a mole of atoms, which is, of course, 6.02 times 10 to the 23rd. And first off, when you look at an individual atom, you see this type of a trend in ionization atom, or energy, or sorry, an individual element. So aluminum loses an electron to become aluminum plus. That's the ionization energy. Aluminum plus loses an electron to be 2 plus. That's the ionization energy. Aluminum 2 plus loses an electron to be aluminum 3 plus, and that's the ionization energy. And then aluminum 3 plus loses an electron to become aluminum 4 plus, and that's the ionization energy. So you can have successive ionization energies. How much energy does it take to remove that electron? So which electron is the easiest to remove from an energy standpoint? Because, oh, by the way, these are not cumulative energies, meaning it takes 580 to go from 0 to +1. It takes 1815 to go from +1 to +2. It would take those two added together to go from 0 to +2. Does that make sense? Okay. So obviously the easiest one to ionize is what? The first one. Takes the least amount of energy. And that's generally true across any element. It's always easiest to remove that first electron because as you increase the charge, you increase the energy. So it takes more energy to increase to a higher charge. But what else do you see here that you might, what kind of patterns do you see in these 4 numbers? Or not patterns. What do those 4 numbers tell you? What do you think you can learn from those 4 numbers? Ideas? The more electrons you lose, the more energy you need. Yep. What about the trend in energies? Does it always increase by about the same amount? It goes up more every time. Is that true? Oh, yes, in absolute numbers, yes, right. So, but does it go up by the same amount each time? Right. Almost. Yeah. So let's look at those differences. So what's the difference between these two? One, about 1240, 1235. Yeah. Okay. Between these, it's much less, right? It's like 900 or 800 and something. No, 925. And then between these two, the delta is huge, right? You have that one? Yeah. Okay. So first, from 1 to 2, the ionization energy goes up, 1200. then it actually goes up by less, and then it goes up by way more. What's happening there? How can we understand that?
It's because once you lose one electron, you have an uneven number, so it wants to not be paired with itself. Or
It's a good thought, but
no,
note that there's actually an energy associated with pairing those electrons. So the other way around. So, yeah, the answer to all of this is we have to look at the electron configuration of aluminum and figure out which electrons we're actually losing when we talk about these successive ionization energies. So here's the electron configuration for aluminum. 3 valence electrons, right? The 3s2 and the 3p1. So does that help explain some of these differences? I think it does. Removing that first electron is coming out of the 3p, which is the outermost electron, leaving a full 3s behind. And that's by far the smallest number, right? 580. And then the next two you're removing from 3s. So 1815 and then 2740. And then how does this explain that jump in that 4th ionization energy? Can we explain that by this through this electron configuration? Which electron is removed by that 4th ionization energy?
One that's making it neon, or the same electron configuration as neon.
Yeah, that 2p electron. So remember here that these electrons are valence electrons, and these electrons are core electrons. So after that 3rd ionization, that 4th one is coming out of the core electrons, which we know are held much more tightly. They're much closer to the nucleus, and so on. So we would expect that that would be huge. So we can figure out how many valence electrons an unknown atom, let's say, has by looking at the sequence of ionization energies and see where the big jump is. Because that's when we stop removing valence electrons, start removing core electrons. So we can look at something like this. Zoom in on that a little bit. This is a table from your book. Here are some successive ionization energies for sodium through argon. So going along the 3rd row, you can clearly tell, and they've made it color-coded for super nice for us, but you can tell by the numbers that that core electron removal, there's always a big, big jump between removing valence electrons, removing core electrons. Ever see that? But what we also see here is trends in ionization energies across the period as well. And this is something known as a periodic trend. We're going to talk about a few of them today. Things that go a particular way as we go across the table and then kind of start over when we go this way. And there will also be trends going up and down. So take a look at these numbers. Do you see a general trend here going from sodium to argon? Is it mostly going in one direction, or is it kind of jumping all over the place? As you go down that list. What do you think? Kind of could say either, really, right? I mean, there seems to be a general trend because it starts kind of lower in the 4, 5, 700s. And then by the time you're at the other side, you're up in the thousands up to 1500. So there's sort of an increasing trend in ionization, first ionization energies. But there's also some going back and forth there. It's not a straight increase every single time. We can look at a graph of that. So here are all the first ionization energies from hydrogen to xenon. As you go across the period, they generally go up. And then when you get to the next spot, so hydrogen to helium goes up, and then you go to lithium, it goes down. Lithium, it sort of generally goes up to neon, and then jumps way back down when you get to sodium. Generally goes up, and then jumps back down. And then within each row, there are these little blips that don't follow the trend. And notice the blip here is in the same spot as the blip here. and actually here also, except it's a little confounded by the transition elements in the middle. Where do you think is causing those blips? Where are those blips coming? Let's label them. So this is lithium, then this is beryllium, then this one is boron. If that's sodium, then that's magnesium, then this one's aluminum. If we go up to the other blip, so we've got boron, carbon, nitrogen. So nitrogen's up here, oxygen's down here. Then aluminum, silicon, phosphorus, and sulfur. Okay, so let's look at that first little, do I have any? We'll get down to that one in a minute. Let's look at this first little blip. Why do you think why do you think beryllium has a higher ionization energy than boron, even though boron is further to the right? Boron should be following this trend going to the right. Well, I guess first we should answer the question, why does, we didn't even talk about this really yet. I put up this statement, in general, as we move across a period from left to right, the first ionization energy increases. Fine, we talked about that. Why do you think that is? Why should the first ionization energy, why should it become harder, energy speaking, to remove an electron as we go from left to right on the periodic table? What changes? If you go from, let's say, sodium to argon, what in the atom has changed? It's not a trick question. Yeah. More protons, more electrons. Right? Okay. So why would having more protons and more electrons increase the ionization energy, make it harder for an electron to leave?
There's more attraction.
Right, exactly. There's more attraction. So within one row, within one n level, all those electrons are going roughly to the same place around the atom, around the same distance. Now we know the p electrons are a little farther out than the s electrons, but everything in the n equals 3 level, let's say, is roughly in the same place relative to the nucleus. So if you've got more protons there, that means that attraction is going to be greater. Electrostatic attraction, that is the attraction between a positive and negative charge, is proportional to the distance between those two. So if they're staying around the same and you've got more of them, you're going to have more of that attraction. So that's exactly why. So then back to this question, if that's this attraction and that attraction increases, what's special about going from beryllium to boron that changes that makes boron a little bit easier to ionize instead of beryllium? What do you think? And do you see a jump in the periodic table there? Like there's a big white space between beryllium and boron. So what does that represent? What's special about going to boron?
It goes from the S's to the P's.
Right, it goes from the S's to the P's. So you've got valence electrons in the S orbitals for lithium and beryllium. You go to boron, suddenly you have valence electrons in the P orbital. So that's what's responsible for that slight difference here, is that boron, you're now ionizing a P electron, whereas beryllium, you're ionizing an S electron. And so it's just enough difference to kind of offset that and buck the trend a little bit. It's even a bigger effect for aluminum. All right, so that said, what about this question? The first ionization energy for phosphorus is 1012, and that for sulfur is 999. So they're pretty close, but that's also against the trend. Phosphorus is a little bit higher than sulfur when we would expect the opposite to be true. So what's happening there? Take a look at the electron configurations for each of those and see what might be happening when you ionize phosphorus versus ionize sulfur.
When you're doing phosphorus, you have 3 electrons, so they each have their own spot.
Okay.
And,
So they're each in a separate orbital?
yes.
Yeah.
When you go to sulfur, one is an orbital with another electron.
Okay. So how does that lead to a lower ionization energy for sulfur?
So if you want to get that electron, you can move it more than.
Right, yeah. Yeah, so everybody hear that? So for phosphorus is 3p. Looks like this, with one electron in each orbital. Sulfur is 3p. Looks like this. So the electron that gets ionized from sulfur, when phosphorus gets ionized, it goes from 3p electrons to 2p electrons. When sulfur gets ionized, it goes from 4p electrons to 3p electrons. So in sulfur, we are getting rid of a pair and leaving a single. And since we know there's an energy cost associated with pairing up electrons, it doesn't cost quite as much energy to take that electron away with sulfur because we're kind of getting that back in the electron pairing energy. So do you see how we start to think about these effects in terms of valence electrons? So knowing these electrons configurations and thinking about electron configurations can really help us to solve some of these issues. Like, why are we seeing this pattern? Well, here's why. We can also think about this the other way. If we're not given the energies, we can predict the trends of the energies. So here are some atoms with some electron configurations. Which one would you expect to have the largest first ionization energy, and which one has the smallest second ionization energy? These, I should warn you, by the way, these types of problems always give people trouble on the exam. They're usually multiple choice type problems. And it's easy to turn things around in your head versus like lowest versus highest energy, first versus second energies, and then thinking about whether something is easier to remove or not. So make sure you're understanding the question really well and write out what it's really talking about. So let's look at the first part of this question first. Which atom has the largest first ionization energy? What do you think of those three? First one? Okay, anybody say second, third? No? Everybody agree? Just don't know. So why'd you say the first one?
Because that would be neon.
Because that would be neon? Yeah. 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 So another way of saying that is that has a full, complete shell, right? That's a noble gas configuration. So removing that electron breaks that fullness, and so that's going to take a lot more energy. Take a lot more energy that way. Which one then has the smallest second ionization energy?
It's the last one.
Why the last one?
Because when you take away the first one, that leaves 3s1. So it wants to go get rid of that 1 to go back to the 2 p's. So,
right. So yeah, they're all going to have higher second ionization energies than first ionization energies. But you're right. In the third one, that second ionization energy is still removing a valence electron. It's removing that second 3s electron. So the first ionization, you take out one 3s. Second ionization, you take out the other 3s. The other two, the second ionization energy will be removing a core electron, or essentially a core for the first one. I guess that's technically a valence electron. So this one will be, we would expect this one to have the largest first ionization energy. We would expect this one have the smallest second ionization. Good? All right. All right, the opposite, I guess, it's not exactly the opposite, but the other side of this is something called electron affinity, which is the energy change associated with the addition of an electron to a gaseous atom. So an atom takes an electron and becomes negatively charged. Electron affinities are given in negative numbers because absorbing an electron gives off energy, usually, in many cases, well, in these cases. So you absorb an electron and you give off some energy. And here's how much you give off. You'll notice some of these atoms just say greater than 0, which essentially means that it costs energy to make these things get an electron. But the ones that are negative give off energies because they want to do that. So we can answer some of the similar types of questions looking at what happens when we remove an or when we add an electron to these different species. So generally, once again, there's a trend. It increases, it gets more negative. We say increases, we mean more negative in this case. As you go from left to right, and then increases or decreases down a group more or less. That trend is not as clear as the left to right trend. But once again, we see some spots that don't follow the trend. And we can probably explain those again using the same types of techniques of looking at the electron configurations. So nitrogen, for instance, is a pretty obvious difference. The electron affinity increases for boron and carbon, drops all the way down so that it ends up being positive for nitrogen, and then gets more negative again with oxygen and fluorine. So what's special about nitrogen adding an electron that costs energy rather than giving off energy? Everybody see it? What's special about nitrogen? We talked about it a little bit in the previous part, but now we're talking about the opposite, so adding an electron. Where do you have to put the electron when you add it to nitrogen? You got it? So nitrogen's electron configuration is going to be helium, 2s2, 2p3. That means when we add an electron, we get (2s2, 2p4).
So you have to pair it with another one?
Yeah, so you have to go to a more paired situation. So it's kind of like nitrogen and oxygen here, just flipped. Same idea because of that, keeping it half full versus full. And then neon, again, it's got a full shell, so that when if you wanted to add an electron, it would have to go into the next valence level, and that would cost energy. So same kinds of ideas. All right, so I guess the last one we'll talk about are these radii, but for ionization energy and electron affinity, the important things to note are that you'll be asked to identify the trends, so to know which ones should have higher than others based on just the general trend, and also to account for the reasons behind these exceptions in the trends. So when we see these little jumps, or it's kind of going the wrong way, or it seems like it should be more, but it's actually less, you should be able to explain that. All right. Okay, so now let's look at the other trends, which is radius, size. The way that we measure atomic radii, we talked about this a little bit last time, but there are what we call covalent radii versus the orbital size radii that we looked at with the radial distribution function. This is essentially saying when this is bound to something, what is the distance between if two of these atoms are bound to themselves, what's the distance between the two nuclei divided by 2? And that's like how much space the atom takes up when it's kind of mashed against something. So anyway, it doesn't matter what numbers we use for our sizes as long as it's consistent so we can compare them. So let's first look at this table over on the left, which is atoms and their cations. I'll try to make this smaller so you can see it all. The atoms are the big sphere in gray, and the cation is the little sphere in red. So first thing you see is that the cations are much smaller than the neutral atoms. Is that what you would expect? It would be, right? Because you've lost electrons. And not only have you lost the valence shell, but you're also now pulling fewer electrons with more protons. So you would expect a condensation of the size that way as well. These numbers in black and red are in picometers, PM. That's 10 to the 12th, or 10 to the minus 12th. So 152 picometers is 152 times 10 to the minus 12 meters. All right, so let's look at some trends. Going down a column is pretty obvious that the radius is going to increase. And we see that. Makes sense because the valence shell is now the next level. So n equals 1 versus n equals 2 versus n equals 3, that's going to get bigger. That's true across the board. Going from left to right, the size gets smaller. So if we go from lithium, and we're just looking at the atoms now, lithium 152, beryllium 112, boron 85, and then 73, 72 by the time we get over to fluorine. We could look at all the sizes in between too, but you see a contraction going across the periodic table. Why do you think that is? If we're adding more electrons as we go across, why are the atoms getting smaller? You kind of answered this before already when we talked about ionization energies. What are we adding in addition to electrons as we go? Yeah, we're adding protons too. So yes, we're adding more electrons, but we're adding them to basically the same place, while at the same time adding more protons and increasing the overall attraction. So those more protons are going to be pulling those electrons in even more, making that atom a little bit smaller. All right. One interesting effect of this, look at the difference between magnesium and aluminum. So this is kind of the jumping over the middle part. The size difference between magnesium and aluminum is 17 picometers. Difference between calcium and gallium, so jumping over the transition metals, is way bigger. You see that? 62 instead, 62 picometers. And that's a function of that. That in this case, the transition metals, you're adding 10 more electrons and protons, 10 more electrons to an inner shell, really, because you're adding them to the 3D. Whereas you're also adding those 10 additional protons, so you have a contraction over that whole series. Contraction over that whole series. And then this thing doesn't go down far enough. But you also see a big contraction throughout the lanthanide series if you get on into the 6th row. That relatively speaking, going from barium over to thallium is an even bigger difference because of those lanthanides, adding those electrons. Okay. So the other trend with the ions is you can see that, first of all, the larger the charge, generally the bigger the effect on the radius. So a 3+ ion is going to generally be smaller than a 2+ ion. It will always be smaller for the same type of atom, but even across different types of atoms, you may see that because of those attractive forces as we talked about. And then the same thing with getting bigger when adding electrons. So O is going to O2 minus. And you see the same trends with the ions, basically. But then, of course, the ions themselves will be bigger than the neutral atoms by quite a bit. So without looking at those, if we looked at these 4 ions, these 4 2+ ions, could you predict the radii, the trend in the radii? Which one of those do you think would be the biggest? I mean, they're all in the same column, right? So you can probably expect that either the top one or the bottom one is going to be the biggest. Which one do you think it's going to be? The what? The bottom one, which in this case is strontium, right? Yeah. Yeah, so we would expect that one to be the biggest. If we go back up, we can check that it is indeed the biggest. All right, I'm trying to find the next thing I have here. So I think I'm missing a picture. There's supposed to be something here, and there is not. Yeah, okay. All right, let's take a look then with the rest of our time here at the hydrogen one more time. And I want you to write down what we actually see and then bring it to lab tomorrow so we can compare it to what you see with the spectroscopes. So let's see, this was helium, that one back there. And we'll get the hydrogen one back. Whoops. I'm going to turn on the lights again so we can get a better. Okay, so do you see those peaks coming up? Those lines from the hydrogen spectrum? See if we can catch some more of them in here somewhere. We're just going to zoom in a little bit, essentially, by bringing that thing closer. So you should see a line up here. If I put my cursor on the tip of that, it's about 659. You can say 660 if you want. Yeah, 659. This one over here looks like it's coming in right around 484 or 485. I guess 485 with rounding. And then I see one at 433. And 4010, not 4010, 410. So it looks like 4 spectral lines. Do you see those on the spectrum there? So if we plug, and I'll let you do this in lab tomorrow, but if you plug those numbers into the Bohr equation, you should be able to solve for which levels the electron has transitioned from to form that particular energy level, or that amount of energy. So in other words, we can convert that wavelength into an energy using, I guess I'll just do it on the screen here. We can use this. We can plug in the wavelength here, get an energy, and then plug that into our there. That B is that negative 2.19 times, I think there's actually a negative here. It's 2.19 times 10 to the minus 19 joules. So you can plug that same energy in and figure out which transitions are leading to these lines that we see. And so if we don't have the lamp tomorrow, we should have at least one actual hydrogen lamp so you can look at it with the spectroscope But I know some of you've got some leaf stuff to do tomorrow too, so hopefully we'll have enough time for everything. Now that I got this thing calibrated, let's see if we can look at the. Did we look at the fluorescent lights in this again? There we go. All right, that's a nice spectrum from the fluorescent lights now. You can see all the different lines, some really narrowly defined lines and some broader ones.